Ceres represents a unique celestial body in our solar system, occupying a special classification and location that sets it apart from other planetary objects. As the only dwarf planet located in the inner solar system, Ceres provides scientists with invaluable insights into the early formation of our planetary neighborhood. Positioned in the middle of the main asteroid belt between Mars and Jupiter, this remarkable body has a rich history of discovery and reclassification that mirrors the evolution of our understanding of the solar system itself. From its initial identification as a planet to its current status as a dwarf planet, Ceres continues to fascinate researchers with its complex geology, unique composition, and the tantalizing possibilities it presents for understanding planetary formation and evolution. Ceres boasts the honor of being the inaugural asteroid ever detected, spotted on January 1, 1801, by the Italian stargazer Giuseppe Piazzi at Sicily's Palermo Observatory. Upon initially observing this celestial body, Piazzi proclaimed it a novel planet, bridging a noticeable void in the solar system that had previously intrigued astronomers. This gap between Mars and Jupiter had been remarked upon by esteemed scientists such as Johannes Kepler, who had famously penned, "I position a planet betwixt Jupiter and Mars." The finding appeared to corroborate both Kepler's hunch and the mathematical forecast known as the Titius-Bode law, which had postulated the existence of a planetary entity in this zone. Originally designated as a planet, Ceres was subsequently reclassified as an asteroid once additional objects in similar trajectories were uncovered. This categorization persisted until 2006, when the International Astronomical Union established the new class of dwarf planets, into which Ceres was incorporated alongside Pluto and other trans-Neptunian entities. This redefinition renders Ceres unique as the only dwarf planet not situated beyond Neptune's path. Even though it is the largest body in the asteroid belt, accounting for roughly 40% of the belt's total mass, Ceres remains comparatively modest relative to other solid bodies in our solar system. With a diameter of 964 kilometers, it is only about 28% the size of Earth's moon and 41% that of Pluto, making its dimensions similar to Saturn's moons Tethys and Dione. The narrative of Ceres' discovery is closely linked to early astronomical theories regarding planetary arrangement. The notably wide gap between Mars and Jupiter spurred astronomers such as Johann Titius and Johann Bode to develop mathematical formulas to describe the spacing of planets from the Sun. When Piazzi located Ceres, almost precisely at the position anticipated by the Titius-Bode law, it initially appeared to corroborate this mathematical model of the solar system. However, the later discovery of numerous other objects in the asteroid belt eventually revealed that, rather than a singular planet forming in that region, the gravitational pull of Jupiter likely inhibited the accumulation of material into a larger body. Ceres possesses physical properties that place it at the boundary between large asteroids and small planets. With a mean diameter of 939.4 kilometers, Ceres dwarfs other objects in the asteroid belt, yet remains small enough that it appears quite dim from Earth. Its apparent magnitude ranges from 6.7 to 9.3, peaking at opposition when it is closest to Earth every 15 to 16 months. Due to this relative dimness, Ceres is invisible to the naked eye except under extremely dark skies, and its surface features remain barely visible even with powerful telescopes. The dwarf planet has a mass of 938,000 kilograms, giving it a density of 2.16 grams per cubic centimeter. This density figure is particularly revealing, as it suggests that approximately a quarter of Ceres's mass consists of water ice. While this is significantly less water than found in the icy moons of the outer solar system, it makes Ceres remarkably water-rich compared to other inner solar system objects. The relatively low density compared to rocky bodies provides strong evidence for a substantial ice component within Ceres's interior structure. Ceres is an oblate spheroid, with its equatorial diameter approximately 8% larger than its polar diameter. This shape is close to, but not perfectly in, hydrostatic equilibrium, one of the defining characteristics of a dwarf planet, according to the International Astronomical Union. Some minor deviations from an equilibrium shape have been observed but not fully explained. Despite making up about 40% of the estimated mass of the asteroid belt, Ceres has only 1/78 the mass of Earth's moon, and its surface gravity is merely 1/35 that of Earth. In terms of orbital characteristics, Ceres maintains a stable orbit within the asteroid belt, completing one revolution around the Sun in approximately 4.6 Earth years. Its position between Mars and Jupiter places it about 2.8 astronomical units from the Sun on average. Ceres is the only widely accepted dwarf planet with an orbital period less than that of Neptune, distinguishing it from the more distant dwarf planets like Pluto, Eris, Haumea, and Makemake, which orbit in the outer reaches of the solar system. The surface of Ceres presents a fascinating mixture of materials that tells the story of this dwarf planet's complex evolution. Remote sensing data from the Dawn mission revealed that Ceres has a remarkably homogeneous surface composition on a global scale. This surface is rich in carbonates and ammoniated phyllosilicates that have been altered by water, indicating significant water-rock interactions throughout Ceres's history. Water-ice distribution in the regolith varies considerably with latitude, with polar regions containing approximately 10% ice, while equatorial regions appear much drier or even completely ice-free. Spectroscopic studies have identified graphite, sulfur, and sulfur dioxide on Ceres's surface. The presence of graphite appears to be the result of space weathering on older surfaces, while sulfur and sulfur dioxide are volatile compounds under Cererian conditions. These volatile materials would be expected to either escape quickly or settle in cold traps, suggesting their presence is linked to relatively recent geological activity. Perhaps most intriguingly, organic compounds have been detected in the Ernetet crater, and at least 11 other regions are candidates for organic material presence. Carbon content in Ceres's near surface is remarkably high, at approximately 20% by mass, more than 5 times higher than in carbonaceous chondrite meteorites analyzed on Earth. This enriched carbon shows evidence of having been mixed with products of rock-water interactions, such as clays. Scientists believe this chemical signature suggests Ceres formed in a cold environment, perhaps even outside Jupiter's orbit, and that it accreted from ultra-carbon-rich materials in the presence of water. These conditions would have been favorable for organic chemistry, making Ceres potentially significant in studies of prebiotic chemical evolution. One of the most prominent surface features on Ceres is Ahuna Mons, a mountain that appears to be cryovolcanic in origin. This feature has relatively few impact craters, suggesting a maximum age of approximately 240 million years, quite young in geological terms. Ahuna Mons' relatively high gravitational field suggests it has a dense composition, consisting more of rock than ice. Scientists believe its formation likely resulted from diaporism, the upward movement of a slurry of brine and silicate particles from the top of the mantle. Interestingly, Ahuna Mons is roughly antipodal to another significant feature, the Curwen Basin, suggesting a possible relationship between these formations. Ceres stands apart from most asteroids due to its history of cryovolcanic activity, making it the closest known cryovolcanically active body to the Sun. Computer simulations suggest that once formed, cryovolcanoes on Ceres gradually recede due to viscous relaxation over several hundred million years. Research teams have identified 22 features as strong candidates for relaxed cryovolcanoes on the dwarf planet's surface, indicating a long history of such activity. Mathematical models suggest that over the past billion years, cryovolcanoes have formed on Ceres at an average rate of 1 every 50 million years. Yamor Mons, formerly called Isolo Mons, represents another interesting cryovolcanic feature on Ceres. This ancient, impact-cratered peak resembles Ahuna Mons, despite being much older. Scientists believe it has maintained its form because it lies in Ceres' northern polar region, where lower temperatures prevent the viscous relaxation that would otherwise cause such features to flatten over time. The distribution of cryovolcanic features is not uniform across Ceres' surface, suggesting complex internal processes influencing their formation. While these features may be linked to ancient impact basins, their exact relationship to impact events remains an area of ongoing research. The cryovolcanic activity on Ceres appears to be driven by the movement of brines through the dwarf planet's outer mantle to its surface. While Ceres likely lacks an internal ocean of liquid water, computer models suggest that briny solutions can still flow through the mantle and eventually reach the surface. The fact that brines reach the surface allows for the formation of cryovolcanoes and indicates that despite its small size and location in the inner solar system, Ceres has maintained some level of internal activity over billions of years. This activity has shaped the surface and created a more dynamic geological history than would be expected for a typical asteroid. Analysis of Ahuna Mons contradicts initial assumptions about Cererian cryovolcanoes. Models indicate that these features must be composed of material far less dense than the average for Ceres' crust, or the observed viscous relaxation that gradually flattens these features could not occur. This finding suggests a complex internal composition with significant variations in density and material properties, further differentiating Ceres from smaller, more homogeneous asteroid bodies in the main belt. The internal composition and structure of Ceres have been subjects of intensive study, particularly following data gathered by NASA's Dawn mission. Gravity measurements from Dawn have generated 3 competing models for Ceres' interior structure, each providing different interpretations of how this dwarf planet is organized beneath its surface. What is clear from all models is that Ceres' active geology is driven primarily by ice and brines, with water leached from rock estimated to possess a salinity of around 5%. Overall, Ceres is approximately 50% water by volume, compared to just 0.1% for Earth and 73% rock by mass, making it a true water-rich world in the inner solar system. The most commonly referenced model suggests a 3-layer structure. According to this interpretation, Ceres consists of an outer crust, approximately 40 kilometers thick, composed of ice, salts, and hydrated minerals. Beneath this lies a 60-kilometer layer consisting of a muddy mixture of brine and rock, followed by an inner mantle of hydrated rock such as clays. The question of whether Ceres has a distinct core remains unresolved. It is not possible to definitively determine if Ceres' deep interior contains liquid or a core of dense material rich in metal, though the low central density suggests it may retain about 10% porosity. Density calculations for the proposed core and mantle crust regions estimate values of 2.46 and 2.90 and 1.68, 1.95 gcm3 respectively. The mantle and crust together are believed to be 70 190 kilometers thick. Importantly, only partial dehydration, expulsion of ice from the core is expected, and while the mantle has a high density relative to water ice, this reflects its enrichment with silicates and salts rather than a complete absence of ice. All layers, core, if it exists, mantle, and crust, contain both rock and ice, though in varying proportions. An alternative 2-layer model proposes that Ceres consists of a core of chondrules, small rounded grains found in some meteorites, and a mantle of mixed ice and micron-sized solid particulates, essentially forming a mud layer. In this model, Sublimation of ice at the surface would leave a deposit of hydrated particulates perhaps 20 meters thick. Depending on the extent of differentiation, this model allows for either a large core, 360 km diameter, composed of 75% chondrules and 25% particulates, with a mantle of 75% ice and 25% particulates, or alternatively a small core, 85 km diameter, consisting almost entirely of particulates with a mantle that is 30% ice and 70% particulates. The unusual composition and location of Ceres provide important clues about its formation and evolution within our solar system. The high water and carbon content, combined with the presence of ammoniated compounds, suggests that Ceres likely formed in a colder environment than its current location. Some scientists propose that it may have originated beyond Jupiter's current orbit, where temperatures would have been low enough to allow the condensation and incorporation of volatile compounds, including ammonia. If this is the case, Ceres would have subsequently migrated inward to its present position in the asteroid belt. Ceres appears to have formed approximately 4.6 billion years ago, during the early stages of solar system formation. Along with Vesta, another large asteroid studied by the Dawn mission, Ceres seems to have remained largely intact since its formation, preserving crucial information about the conditions and processes of planetary formation in the early solar system. While both bodies formed during the same period, Earth-based studies indicated they developed with very different and complementary compositions. Vesta appears dry and rocky, while Ceres shows evidence of significant water content with briny water below its dry surface and numerous bright salt deposits. The thermal evolution of Ceres was significantly limited by its small size. Smaller bodies cool more rapidly than larger planets, which restricts the degree of thermal differentiation and geological activity they can experience. Despite this limitation, Ceres appears to have undergone partial differentiation, developing distinct layers with varying compositions. The presence of hydrated minerals throughout Ceres indicates extensive water-rock interactions during its early history, suggesting that liquid water was present within the dwarf planet for a significant period. Over its long history, Ceres has experienced numerous impacts that have shaped its surface. The fact that the surface has preserved craters almost 300 kilometers in diameter indicates remarkable structural stability. The outermost layer of Ceres is estimated to be roughly 1,000 times stronger than water ice, which is consistent with a mixture of silicates, hydrated salts, and methane clathrates containing no more than 30% water ice by volume. This strength has allowed Ceres to maintain its overall structure despite billions of years of bombardment in the asteroid belt. Our understanding of Ceres was revolutionized by NASA's Dawn mission, which arrived at the dwarf planet in March 2015 after previously studying the asteroid Vesta. Dawn made history as the first spacecraft to orbit two different extraterrestrial bodies and the first to orbit any dwarf planet. Powered by innovative solar electric ion propulsion, the spacecraft conducted extensive remote sensing observations of Ceres using a suite of scientific instruments. After completing its prime mission in 2016, Dawn continued in an extended mission, gathering additional data about this fascinating world until the mission's conclusion. Before Dawn's arrival, knowledge of Ceres's geology was limited to spectroscopic studies from Earth orbital and ground-based telescopes, which had only tentatively identified the dwarf planet's overall surface composition. Thermodynamic models of Ceres' interior and evolution had been constructed based on properties such as its shape and bulk density, but these remained largely theoretical. The data returned by Dawn confirmed many earlier predictions, while dramatically enhancing our understanding of Ceres's composition and evolution, effectively transforming it from a largely astronomical object to a geological one with a complex history. Dawn's detailed observations revealed numerous surprising features, including the bright spots in Occator crater, which were determined to be deposits of sodium carbonate and other salts. These deposits provided strong evidence for the presence of briny water beneath Ceres' surface that had reached the surface in the geologically recent past. The spacecraft also documented the dwarf planet's cryovolcanic features, impact craters, and varied surface mineralogy, painting a picture of a dynamic world that has experienced significant geological processes throughout its history. The scientific significance of Ceres extends far beyond its individual characteristics. As a body that appears to have formed in the cold outer solar system, but now resides in the asteroid belt, Ceres provides crucial evidence for the migration of planetary bodies during the solar system's formative period. Its substantial water content makes it one of the most water-rich bodies in the inner solar system, offering insights into the distribution of water throughout our planetary neighborhood. Additionally, the organic compounds and high carbon content detected on Ceres make it potentially relevant to studies of prebiotic chemistry and the origins of life. Ceres stands as a unique world within our solar system, occupying a special niche between the smaller asteroids and the larger terrestrial planets. As the only dwarf planet in the inner solar system, it provides an important counterpoint to the ice-rich dwarf planets of the outer solar system, like Pluto and Eris. Its substantial water content, evidence of past and potentially ongoing geological activity, and complex internal structure all point to a world that has experienced a far more dynamic history than most of its neighbors in the asteroid belt. The exploration of Ceres by the Dawn mission has significantly advanced our understanding of this fascinating world, transforming it from a distant point of light into a geologically rich body with a complex evolution. From its impressive cryovolcanic features to its water-altered mineralogy and evidence of subsurface brines, Ceres reveals processes that bridge the gap between the geology of rocky inner planets and the ice-dominated worlds of the outer solar system. As we continue to analyze the wealth of data returned by Dawn, Ceres will undoubtedly continue to provide valuable insights into the formation and evolution of our solar system. The story of Ceres is also the story of our evolving understanding of the solar system itself. From its initial classification as a planet to its redesignation as an asteroid, and finally as a dwarf planet, Ceres has challenged our categorical boundaries and forced scientists to reconsider how we define and classify the diverse objects that orbit our sun. As we look toward future exploration of small bodies throughout the solar system, the lessons learned from Ceres will help guide our investigations and deepen our appreciation for the complex processes that have shaped our cosmic neighborhood over the past 4.6 billion years.